Okay, hello everyone. Thank you for being here. Today we have Andreas with us, and we're going to start in a couple of minutes. We're going to start with a quick, very short presentation about who we are, what are we doing today, and then we go from then. Awesome. So first of all, I have to thank. Hello everyone. Special thanks to Andreas for replying back to me so fast and made this whole workshop possible. Also, the workshop will be recorded, and the recording will also be accessible to everyone who's gonna be participating in the hackathon, during the hackathon, or after that. So it will be sent to everyone as well. Thank you so much for being here. I know it's this is our first time kind of streaming everywhere on LinkedIn, YouTube, and Twitter at the same time. So we'll see how it goes. So a little bit background about what are we doing, who we are. We are Beloud. If you didn't know what I'm doing, I'm co-founder of Beloud. Beloud is a startup studio and accelerator. We help startups go from zero, finding their next 10K customer or raising fund. And the accelerator, if you have a startup already, if you have a team, you can join in, and we can support you more. If you don't have a team but you have an idea, we can become your third co-founder, and we can help you with realizing your idea. We also have a great community all around the world, and a community of startup founders, creators, and investors. And we host programs, workshops, events such as this to engage with our audience and give more value to our audience. We are on a mission to onboard the next generation of creators, builders, and investors to the imagination age. But what is imagination age? Well, you remember like the time of Facebook when it was a thing back then. It was really exciting to send messages to other people and send emails to other people. Well, that was in the past, and that was called information age. Now we are entering a new era that's called imagination age. Imagination age is the idea that right now we have abundance of access to resources and knowledge, and we can literally realize any ideas that we have in mind with these technologies such as AI, AR, VR, Web3, creator economy, and more. So right now, the most important thing to have is an idea to create and realize something. So also, we learned about this. Someone had an interview recently, and he was talking about that. I'm going to play it quick.
Yeah, the sound isn't coming out too much, but essentially what he's saying, as you can see in the subtitles, you can make the next billion-dollar startup in AI. And that's what Sam Altman and his buddies are betting in their group chat. What we decided is that in the world where you can go from prompt to anything in seconds, and you have this opportunity to make the next billion-dollar startup, can you come and do it in 3 days? Hence, Be Loud and Build. It's a 54-hour AI hackathon. May 10, 11, 12, to go from one idea to an MVP to a user. We have Andreas from Neo4j joining us today to give us a hands-on insider look into how to make smarter RAGs and how to use knowledge graphs in your RAG system. I'll pass it on over to Andreas, and thank you so much for being here again.
Thank you for having me. Thank you both. And it's great to be here, and I love what you guys are doing with Be Loud. So I'm really happy to be a part of this community, and hopefully I can provide some useful information to everyone who's going to participate in this hackathon. And of course, hedge your bets that you'll be able to win. If you use the stuff you're going to learn today. So let me see if I can start with some sharing my slides first, which is forever how everything always starts, is just properly sharing. Oh, nicely done. Okay. Cool. So there's my slide one. So knowledge graphs for RAG. In fact, all of that might need some explanation. I will go through all this from kind of ground, from an initial understanding of what this stuff is onto actual practice and how you do this stuff in the real world. And actually, I'm going to back up here again, just for a second. So I am Andreas from Neo4j, or otherwise known as ABK of Neo4j. I've been with Neo4j, which is a database company, for quite some time, since it was an open source project. I haven't quite gone from 0 to 3 days into $1 billion company, but we've been doing pretty well as a database company. And I've been along for some of that ride. So I've seen from the early days, I was employee 10. So we're now at just over 800 employees. And so I've seen quite a transition within the company. And I'm happy to share anecdotes and history about any of that stuff if you guys are interested later on. But for today, we're going to be focusing on generative AI. And the place to start with any kind of talk about generative AI, of course, is the memes, because the memes help us understand the world. They're great metaphors, great analogies for understanding what's going on. And these are the 3 memes that I love the most. I think the most popular one, over the last year has been the kind of stochastic parrot aspect of dealing with Gen AI, where it's, LLMs are just these incredible machines, or these, animals, I guess, these parrots that have just learned everything that people are being saying on the internet, whether that's Wikipedia or Reddit. They've just heard a bunch of stuff and they just repeat it, sometimes randomly, sometimes inappropriately, but they don't know anything other than what is public knowledge. So there's that aspect of it. The kind of stochastic parrot is what's really referred to. A little bit different than that is this idea that an LLM is really a sock puppet. Because when you're talking with an LLM, when you're using ChatGPT, it reflects you. It reflects the person who's holding the sock, right? Like, you're really talking to yourself when you're talking to ChatGPT. It's yourself if you happen to have read the entire internet. So the things that you say and how you say it influence what it says back to you. That at the end of the day, what these models really are fantastic autocomplete engines, right? So they're really just trying to anticipate, like, for what you've typed in, what's the most likely continuation of the text you've provided to it. And that simple process really is what opens up wonderful opportunities that we'll explore today through RAG. This other metaphor that's here isn't as common, but it's my favorite one for the purposes of RAG. It's this box in the back here, that it's really alien technology, that LLMs are basically sci-fi alien technology that has landed on the Earth. And as with all sci-fi movies, somehow, mysteriously, magically, humanity's figured out how to plug into the power source or the engine or whatever it might be inside of an alien spaceship, and then use it for actually doing stuff. It's always a bit unbelievable when it happens in sci-fi, but it's really what's happening, with anything that you build with Gen AI these days. Within all those metaphors, it's this bottom 2 that really ends up being the kind of starting point for getting into doing things with RAG. That when you're doing a chat application, even if you're doing some prompt engineering, you're handing over to the LLM at the end part of it. So it's the G part of RAG, is the generation part of it. And you don't really know what the LLM is going to do, and you can't really necessarily explain what the LLM has done. So trying to fix that part of the problem. And also that it only knows about public knowledge. So that's the R part of RAG, is actually retrieving some extra knowledge that might be private, that's in a database somewhere or some other data source, and providing that to the LLM so that it can expand what it knows about, and then maybe reason about that or not, maybe do some summaries or things like that. So how do we integrate with the alien technology? And in practical terms, this ends up being, what does RAG really mean? Let's dig into that. So as an acronym, you've probably all heard this before, but to say it out loud again and remind ourselves, it's retrieval augmented generation. It sounds very fancy. Oh, someone forgot to press the live button. I don't know. Is everything broadcasting properly or not? But however you can, I'll just keep talking. And if there's anything I need to do to adjust, please do let me know.
Quick comment. Yes, it's being live. I think you can also press live so it goes live on your channels. If you see the option, feel free to press it. If you haven't, totally okay. It's being streamed to YouTube right now, LinkedIn, and Twitter.
Okay.
Yes.
I see that I'm live. I don't see any other button. Oh, okay. Thank you, Noreen. Okay. Nora from our team is here as well. She's on top of it. Thank you. All right. Appreciate everybody giving me a little bit of a technical break there to make sure we're all sorted out. Okay, so let's get into RAG itself. And this is the general framework for RAG. This is how you think about it. It starts with just what does a chat application itself actually look like. You start with some kind of a user interface where somebody can type something in, and you take that user input and you really just pass it to the LLM just as it is. The LLM does some stuff with it, figures out what it wants to respond to, and then you provide that back to the application, and that's the entire process of just chatting with an LLM directly. Now, RAG basically interjects at that first stage when you get the user input from a user interface. You don't hand that directly to an LLM. The first step is you take the user input and you decide, okay, based on what I've got here, I might have a couple different strategies for how I might be able to provide an answer. And one of those might be I want to query a database. And so maybe you do query a database, you get some information back from the database. At the end of that process, you actually package up whatever you got back from a database back into text, back into a prompt, then still pass that to the LLM. So you pass the original user question plus the extra information you got from a database, which ends up being context for the user prompt. Pass that all to the LLM. It still does the generation part of it. That goes back to the user, and that's the complete kind of round flow. When you do that, you've already extended what's available to the LLM, what it knows about, because you've queried a database, hopefully gotten some extra information that is particular and useful for the question that the user asked. And that will be because you've provided more particular specific information, it reduces the possibility that the LLM is going to make stuff up. Now, I must caution at this point, there's still a bit of prompt engineering magic going on that you need to make sure that the LLM does its best to only give answers based on what you've provided it. Don't go outside of those boundaries. That's still very important. But we're going to focus on how you actually do the retrieval part and not so much of the prompt engineering. If you think through that kind of workflow, there's information that's available at a bunch of different layers. And when you're building an application, I really encourage you to think about each of these layers very carefully because they all influence the quality of the application you end up building. It's very easy to get fixated on just like, what are you doing with the LLM? And maybe even what are you doing with the database? But take the time to remember at the end of the day, there's a user at a keyboard who wants to do something. Make sure that what you're providing them is relevant and helpful for what they're trying to get done. So they know something about what they're asking and why they're asking it. Your application, of course, knows something about the context within which the user is talking to the application you've built. So, you will have given your application a name, for instance, that already set some expectations about what to expect out of the application. And if the application is talking to a database, of course, the database knows some things. And then the LLM itself has general knowledge about whatever it happened to be trained upon, right? For developers' purposes, like if you're a software developer and building a RAG application, it's this middle part. This is the part where you have the most control. You control what the application is, of course, and you can control what the database looks like and how you interact with the database. For that part there, and starting with thinking about what the data itself might look like, it really ends up being kind of a mix of things. And for most people, when you think about chatting with an LLM and creating a chat application, the extension of the knowledge is often based on hey, can you chat with a PDF, or can you chat with some markdown documents or something? And this is sometimes called unstructured data. So whether it's in PDFs, plain text files, or even if it's images, this is content that isn't really structured, but there is information that's there. And you want someone to actually integrate that information with the LLM to provide answers. So there's pure text. In kind of information retrieval terms and computer science terms, you think about this as a specialization of information retrieval, where what you're really doing is information search. Your assumption here is that the question somebody's asking has a direct correlation with an answer somewhere in the text that's available, or maybe in the images or something like that. And so you're really just kind of doing matchmaking here. It's like, okay, for this question, what is the most likely part of all the information I have here that has the answer? Let me find that, pass that back to the LLM, and let it figure out what it wants to say. So that's information search. This is where people usually start with doing chat applications. On kind of the extreme other side, since we already have structured data in many places, whether it's in just a database or it's a data warehouse or a lakehouse or something elaborate like that, or even through an API, there is structured data that exists as well. And that, of course, has lots of really useful information. And typically this is just, you've got a database somewhere or a data warehouse, and you want to figure out how can we take the user's question and get information from that might be relevant to answering the question, and then provide that back to the LLM, again, to package it up into an answer. So structured data, the kinds of questions you do here, again, this is, in computer science terms, it's still information retrieval, but now rather than just kind of doing a lookup or a search for something, you're actually running a query. So this is where you would take a natural language question and try to turn that into a database query. And you'd be able to ask things like, here in the example, you could say, all right, how many iPhones did Apple sell in this quarter? That may not exist in just pure text somewhere, but it probably exists in a database if you have information about companies and what their sales look like. And that actually ends up being a database query. So if you can turn the natural question into a database query, then you can get those facts back, pass the facts to the LLM, and again, make it more likely that it's not going to make stuff up when you provide an answer to the user. There's still a very small chance that the LLM, being an LLM, is going to be creative and maybe turn it into Shakespearean prose or something, even though you've asked for very strict information back. In the middle, it turns out that you can actually kind of mix the techniques you use, both for doing information search and for doing information query, and combine those data sources, and in one request, actually find new things and ask new kinds of questions. Sort of in the wild, this naturally occurs if you've done something like created a WordPress site. If you think about what a WordPress site is, you of course have lots of basically web pages or blog posts or something like that. So you've got a lot of text, and so that gives you that element of it, which is fantastic. But all that text is usually within structured data as well, and so you have a mix of structured data and unstructured data that you can query at once and provide answers. And this becomes really powerful. Here, it's not just that you can just fetch things. You could do that if you want to. It's not just that you turn, a natural language into a query. You can also do that, but you can combine those techniques because you have a little bit of both and they're all in one place. So for example here, in this question, I guess we're focusing on kind of companies and like what their investors are concerned about. If you were doing market research, you might be able to ask, which investors will be impacted by a chip shortage. So if you had information about companies and what their business risks are, you'd be able to do kind of a natural language search for that and find out what companies are impacted. But then from those, you might want to be able to like trace back to who are the investors that invested in that company. And then you'd be able to realize what are the investment portfolios that are exposed if there's a chip shortage. So if you're doing market analysis, this ends up being really helpful when you're trying to do impact of like, some real world event has happened that's going to affect, chip production. And you can kind of trace all the way back to like, okay, who are the investments? What do you need to, change in your portfolio to not be caught short with changes in the market? When you do combine all of this into one database and have queries that query across this is very particular that the data model that you end up with is what's called a knowledge graph. And it's a knowledge graph because the queries that you end up writing when you're going from a natural language into querying this combination of either pure text, pure data, or a combination of them ends up being really patterns of data where you're not looking through, let's say, if you had tables, you're not looking through a table of things. You're looking for particular records that might have some data over that are connected to some other, information that's connected to some more information that ultimately might have some pure text and combining all that in one query. So you're really querying across things, which is really a graph pattern, whatever the data source originally might have been. So for us at Neo4j, we as a database, this is our primary way of thinking about the world, modeling the world, and querying the world, is what's called a knowledge graph. In a RAG application, if you have a knowledge graph, the access patterns for accessing that knowledge graph and mapping from a natural language to like the queries that you run on the database to get the answer from that is called graph RAG. So it's a couple different strategies for how you do the information retrieval. And it's the ones that I just mentioned. It's information search, information querying, and information discovery. It basically ends up looking like this. If you're doing just kind of sort of information search, you're basically doing an index lookup, whether that is a vector search, a geospatial search, or full text. Vector search is where people will usually start when they're doing, question answering with an input prompt. But you find relevant documents there, and that comes back. On the data side, the graph query is directly trying to, generate a structured query from the natural language question. And in the middle here, you're either predefining some of the queries that you might want to run that correlate with some text, or you're doing that dynamically, that you're finding some text and finding a context around that text that adds extra information that might be useful. And I'll show some examples of how that actually works out. Okay, I'm going to take one step back here. That was kind of the context within which what we're talking about with knowledge graphs and graph RAG, that you have this idea of pure text, pure data, and then doing a mix. I'm going to get down to some of the details now about what a knowledge graph looks like and how you think about doing the data modeling for it. And very conveniently, it starts off pretty easily. It's like doing relational modeling, if you've ever done that in your life as well, that you start with just like, what are the things you have? And here in this example, I'm going to start with thinking about Stack Overflow. If you think about what Stack Overflow is and what are the things you have in Stack Overflow you might want to model in a database. You've got questions, you've got answers to those questions. Of course, you've got users, and you also have tags. Like the questions come in different categories, right? You can tag a question being about, let's say, RAG or knowledge graphs, right? And so that's the fundamental thing. You start with data modeling. It's just, what are the things you know about? Because this is data modeling and because we're dealing with the database, for each of those things you know about, you know that they're actually data records. And so for each of these records, they can have arbitrary kind of key value pairs essentially attached to them. We call them properties in a knowledge graph. So the questions might have titles, they have a body, they'll have like a URL that links back to, the original website where, maybe the data came from. For users, strings for the name, maybe what their current reputation is, that's useful to know as well. And for the answers, what was the answer, and was it accepted or not is maybe enough. And tags end up being just simply strings in this data model. But that's pretty straightforward. This is just, here's a couple different types of records we know about and the information that we store about them. To make that into a graph, of course, classically, you end up using both the circles and the arrows to say that actually we know that not only are these things information we want to keep track of, but we know that there's relationships among them. One of the key kind of insights about graphs is that you start very easily with the data modeling that I was just describing, and you just capture the things you've got. And then you just realize that not only do these things exist there, but there are both implicit relationships that you can make explicit. And once you do, there's really interesting patterns emerge. So I'm going to kind of talk through that. The first step is to say, all right, we know that users ask questions. So we have a relationship from the user that asked questions. A user also provided an answer potentially, and that answer answers a particular question. And the questions are tagged with some kind of a tag. This is a very simple data model, and you can kind of start at any point within this graph and just follow the arrows and kind of read it out loud as if it's sentences. That's a key aspect of knowledge graphs and part of what makes them so much fun to work with in terms of a RAG application. So patterns end up emerging that you can then do work with. You can reason about them. You can actually then map them also to natural language questions. As I was just suggesting, you could say that we know that these users asked a question. It's a very simple pattern, just from users to questions. Users provided an answer. If you'd write either of these things I just mentioned in kind of plain text, you would end up probably using parentheses around the user, and then something of an arrow that goes through provided that goes to some kind of an answer. You can continue to do that, as long as you'd like to extend the pattern. So here I've gone from some answer that answers a question that was tagged with a tag. And what's lovely about this, as I mentioned before, this looks pretty readable. And as you read this out loud, if your knowledge graph that you're modeling sounds right, if it sounds like something rational and reasonable to say, then it's probably a well-formed knowledge graph. And in a graph RAG situation, dealing with an LLM, with Gen AI, it maps really nicely to natural language questions. It's a really key aspect of having a knowledge graph around. If you were to take those patterns and turn that into a query language, it would look something like this. We have a query language that's called Cypher for Neo4j. It is our own query language that, as of last week, actually, now has become an international standard language. There's the International Standards Organization, the ISO committee, the same committee that some 40 years ago created SQL as the dominant language for database queries at that time, has only now introduced a second language that is sufficiently unique from SQL that they've realized it actually is its own category of language, that while you can do some aspects of this in a relational database, the query language itself and the concepts within it are so unique that it's become its own standard. This is a really amazing thing. It looks like this. The bottom half of the screen here takes the idea of those patterns that I was talking through, and in an SQL-like way, you have different clauses within the query language. So this first clause here is a pattern match clause. I say match, and then here's the pattern I want to match. Match answers that answer some question, and I'm going to assign A to the answers and Q to the questions, and then just return those Q and A pairs and limit it to 10. Pretty easy to read, pretty easy to write, and again, maps pretty nicely to natural language questions. And because we're doing Gen AI, I have to also mention, as a database, you can also, for any point where you have text, create vector embeddings of those text, and then do searches across those, a classic kind of vector search, where vector search is vector similarity search. I'm not going to get into the details just right now, but if you have any questions, please ask in the comments. I'm happy to talk more about what a vector is and how a text embedding actually works. But the idea here is that in the kind of normal pattern of having a chat application, if all you're going to do is just take a user question, calculate a vector embedding for that, and then find out where the answers might be, you can do that with a graph as well. And it works the same as it would for any other database that has a vector search. Okay. I'm going to get into a bit more concrete example now, which is one that I actually have some notebooks for as well. But before I get into that, I'm going to pause for just a second and check through the comments and see if there's any questions that came up that I should try to answer.
Quick question.
Yeah.
Could we get a link to the notebook so we could like share it with people if they want to like go through them right now? Just because we have you right now, it'll be easier if they have any questions to ask you.
That's a great idea. Yeah. So what I'm going to do is I'm going to jump forward to the link and wait, see if I can. I'm going to leave it on the screen and also copy and paste it. Switch to here. I'll copy it into the comment section so people can hopefully click it directly.
Thank you.
I cannot post comments on LinkedIn. What have I done?
Did you want to send? I could just type it in right now and.
Let's see.
Okay, I just posted it here, so it's on YouTube right now, and I'll manually go over to LinkedIn and like put it there as well.
Perfect. Appreciate that. Thank you so much. I see questions come in from Varun. Let me just answer that first. To get the relevant context from the graph, should we store the text as a node property? Yeah, you definitely should. And I'll talk about this in more detail in just a moment when we go through this specific example using the Gen AI SEC Edgar data set. So I'll talk about that exactly as I go through the next couple of slides. Erwin, you also asked a question, do you think it would be efficient to insert little functions of code into the nodes to query a node instead of a list of data? That's an interesting idea. I know that some people have actually tried to do things like that and actually use the graph not only as data, but also as describing workflows and compute. I think depending on the data set that you're working with, that ends up being helpful or not. It depends on how kind of agentic you are in the approach that you've got. I think if you have very complex workflows, having those workflows actually encoded in the graph can be very beneficial. That's kind of like next level stuff that I'm not going to get into today, but I think there's some really great possibilities around that. Cool, and hopefully people can get over to the those notebooks. I will say those notebooks are live. I was working with them today and realizing that I've gotten kind of out of sync with the data model and some of the examples. I think they are up to date now. Oh wait, I haven't. I'm going to go make sure I pushed out my changes. Okay, I won't push out my changes quite yet. But if people try out the current code, I might have local changes that I haven't pushed out to GitHub yet. And when I get to the end, I'll check that to make sure it's all up to date. Okay, let me move forward a little bit. So the data set that I'm going to talk about and then do some demos around is from the SEC. This is in the US, the Securities and Exchange Commission. This is where anybody who's publicly traded as a company, you've got to file with the SEC to describe, there's a particular form 10K that if you're a publicly traded company, you've got to send it into the SEC describing what your primary business is, what the risk to your business is, the last quarter, what it looked like, all those kinds of things, so that anybody who might want to invest has, easy accessibility to that stuff. So there's that component of it. And from those Form 10Ks, because there's a lot of really interesting text there, that's what I'm using for unstructured data. That's where we're going to pull out all that text, add that to the graph, and then I'll show you actually the technique for that in just a couple of slides. But that'll be the unstructured data. There's also another set of data called Form 13, which is filed by institutional investment management companies. Large investment companies that have giant portfolios where they invest billions, millions, possibly, I suppose, billions of dollars into publicly traded companies. They also have to file I can't remember what the bar is, but if it's like if they have over, I think like $100 million in investments, maybe it's something like that, they have to file and describe what they're investing in, both who the company is, the number of shares they own, and also the value of those shares. For that, we don't care so much about the text of what is being filed for those companies. We do care about all the individual investments themselves. That ends up being really interesting for asking good questions about market research. And so that turns into structured data instead. So for all the data that's in the Form 13s, what we've done a bit of data preparation for, that we're not going to go through today, but the result of the data preparation ends up being a CSV file that has one row for this company. They invested X number of shares at Y number of value into some other company. And then there's just row after row of that. That ends up being what we end up using for creating the knowledge graph and then doing queries on it. The mental model I highly recommend for thinking about creating a knowledge graph is different in kind than if you've done, again, relational modeling in the past. It is very different thinking about a graph. When you do relational modeling, there's this pressure sometimes, or maybe this concern about trying to have a very good data model that anticipates all of the queries you might want to be able to run on it. So you have to do a lot of upfront planning and have a good model, because data migrations are really annoying. Adding to the data model is really annoying. So you want to kind of define all that up front. With a graph, you tend to not do that. With a graph, it is highly recommended to start very small. And here I'm just playfully calling it the minimum viable graph. Create as small of a graph as you can that can answer some useful questions, and then just kind of iterate on that. And the iteration that I recommend is that you create some data, you look for a part of that data that is useful for enhancing in some way. So usually that it means adding some kind of an index, and then connecting that data either to itself or to other data that you already have, and just slowly repeating that process over and over, but being driven all the time by questions that are being asked that you're not able to answer. That I think is incredibly important. There's again, in sort of software development terms, sometimes people think about like doing this test-driven development where you write tests first, figure out what the tests are that are failing, and then you go fix that test. That's how you generate code, right? You write code by, creating things that don't work, and then you make them work. The kind of Gen AI equivalent of that is just build something that works at all, and then start doing evaluation. So you'll hear people talk about eval. That is the Gen AI version of doing testing. When you're doing that, write some expected questions, what the expected answers might be. Make sure that the system that you're building is able to answer those questions. And when you get to people asking questions that aren't in your list, add them to your list. Let that actually fail, and then figure out how you can answer those questions, so that over time you kind of grow a body of questions and also a data model that fits what people are actually doing with your data. Don't try to anticipate too much up front. The place to start here, the easy place, is with the Form 10Ks. Again, this ends up being the unstructured data. This is from the publicly traded companies themselves. And this is common across all databases. If you start with a bunch of text, let's say you've got, thousands, millions, whatever it might be of, documents, whatever the data might have been, PDFs or whatever, you take all those documents and you chunk them up. Typically, you don't take them exactly as they are. You split them up and you store each of those chunks individually as data records inside of a database. And you do that for two reasons. The initial motivation here is when you're dealing with an LLM, people are always concerned about like the context window. And I know that context windows are growing, and that there's some really fantastic papers about how you can potentially have like an infinite context window and things like that. So the pressure to have a small context is kind of lessening a little bit. Probably over time that will disappear. But the other motivation for chunking things up is to have chunks that mirror the kinds of questions that people are going to ask. You want to have really finely, mapped, I suppose, chunks that are very likely to mirror the question somebody's going to ask. This is because sometimes if you provide, even though you can provide lots of context, if you provide lots of context and the question isn't very specific, then the answer might be less and less appropriate and actually, tend to hallucinate a little bit. So the closer you can have a match from like, here's the question that somebody asked, and here's exactly the answer, and it's like 1-to-1, and it's not a whole lot of context at all, it is less likely that the LLM is going to hallucinate, because it doesn't have extra text to get distracted by. It knows exactly what's there. You can say, hey, here's the answer to the question. Write that in, again, maybe Shakespearean prose, but don't do anything else. That's really important, even at this stage. Okay. moving forward a little bit and thinking through the process, you split up the text into different chunks. These are different data records. For each of those data records, the typical thing to do at this point is to create vector embeddings. And again, this is just a process of really asking typically an LLM, hey, given this chunk of text, can you turn that into an array of numbers where that is placing it inside of a vector space? And I'll put aside vector space for the moment unless somebody has any questions about it. So great, you do the vector embedding, you store that in the database as well. In Neo4j, this is something that happens natively. So each of these chunks end up being nodes inside of the graph, nodes that are not yet connected to anything, but they're nodes anyway. And each of those nodes will end up having two properties. We'll have the text that was part of the chunk, but also then the basically floating point array that is the vector. Those will both be properties that will be visible inside the nodes themselves. To make it a little bit more graphy, and also this is useful, you then can at least connect those chunks to each other. You know that they occur in a sequence, preserve that sequence in the graph itself. You end up creating basically a linked list where it's chunk, next chunk, next chunk, next chunk, next chunk. That ends up being able to recreate the entire series of chunks if you want to. This is very useful for a couple of different reasons. Here's the overall process that I just kind of talked through maybe a little bit quickly. But we started with some raw data. We split up that raw data, created some records out of that, created a vector embedding for those records that we created, and then connected them together. This is the minimum viable graph for this data set. Create some stuff, enhance that stuff, and then connect it to each other. That's a perfect place to start. This data model here on the right-hand side, the chunk with a linked list to the next chunk, is other than a graph that has no connections, this is the smallest graph you can possibly create. Just a linked list of things is pretty simple. Even here, you already get some nice advantages. You can do a vector search, of course, because you've got the vector index you've created there. So that's really lovely. And because you have this linked list that things occur in, you have an arbitrary kind of context window that you can select. So once you land on a chunk, you can decide for that chunk, give me 3 or 4, however many chunks before it and chunks after it you'd like, whatever's appropriate for how your chunking strategy actually looked like. That gets you the exact text that matched, and then maybe a little bit before and after as you would like to. That's good for answering questions and providing that context all the way back to the LLM. If you're building a user interface, it's also super nice and convenient that you can easily then just kind of page through things. So if you're providing the user not just with the LLM's response, but maybe the original text itself, in some contexts, that matters more than the LLM generating stuff, but what is the text? You now have the opportunity to very easily create a user interface that lets people just page easily forward and back through the chunks. It's really nice. Okay, that's the simple graph. One small elaboration of that graph and this idea of kind of iterating on the knowledge graph. We know that all those chunks came from some form, that they all originated from someplace together. So let's recreate that inside of the graph. For each of the forms that we know those chunks came from, we'll create a form node as well. And each of the chunks will have a relationship back to that form. So if you land on a chunk, you know that it's a part of some original form. And it's on that original form we're going to put the metadata that is common across all of the chunks. So, what was the original source of the form? What any other kind of metadata, like hear about, like maybe what was the company that filed it, things like that. That's the place to put it, is on this parent node here. Also in the parent, it's a really convenient place to also do things like, well, provide a summary. You can turn back to the LLM and say, actually, for all these chunks that I have, create a summary of that, store the summary on the form, and create yet another text embedding for just that summary. Now you've got two strategies available for answering any given question. You can decide, do you want to ask both of these things, both the forms and the chunks, for a user question? What's the most similar chunk, and also what's the most similar form? And you can figure out which one of those might be most appropriate for answering a particular user's question. Sometimes it's more helpful to actually have the summarization of it. Depending on the content that you have where you've started, you might end up with multiple levels of summaries here. So if you have a hierarchy that goes from chunks, it goes maybe up to, let's say, chapters, and then from those chapters up to sections of a book, and from the sections of a book all the way up to a book itself. Maybe that book is part of a library. At each of those levels of hierarchy, it is very useful to actually create summaries at that level, and then also do text embeddings of those summaries. This is purely just taking advantage of the natural kind of organization that we know is inside of content, and providing opportunities for actually answering different levels of questions, often different abstractions of questions, depending on what level you actually want to go in the hierarchies itself. going all the way over to the structured data side of things. This was the Form 13s. This is the investments that these management companies have made into particular public companies. Again, this is coming from CSV files. We're going to create just pure data out of this. We're not actually going to do any vector embeddings for this because we don't have a lot of text to deal with. Instead, what we're going to do is create records for each of the management companies themselves. So here, they're called managers, and then the companies here on the right-hand side, the green rather than the cyan, I suppose, in the color scheme here. The green nodes end up being the public companies themselves. So each of these management companies owns some amount of stock in these companies. This pattern from manager owns stock in company, each instance of that pattern correlates with one row in the CSV. So you just kind of iterate through the CSV, and for every row that occurs there, you either create or find a management node, create or find a company node, and connect them with this investment of an owned stock in. So for every management node that's connected, there might be multiple companies that they've invested in. And also the converse is true, that for a given company, there's multiple number of managers that maybe have invested in that company, but they'll all show up as different, as exactly this pattern within the graph. On the manager side and the company side, we add a full text index here, because if you're answering questions about public companies, it's more helpful to allow users to have accidental misspellings of a company's name, or like maybe the case sensitivity also comes into play here. That is more helpful than having conceptually similar names. Like, so if you've mistyped Apple, you don't want banana to come up because it is conceptually similar. You want Apple, the company, to come up, and that is actually a textual difference rather than a conceptual difference in the name. So that's why I use full text indexes here, and that's the strategy for actually querying this kind of data. Start with a full text index, then find patterns around this as well. There's one more opportunity that we can elaborate on here. In these filings, we happen to know what the headquarters are for both the companies and these management institution firms, and we can pull those out to separate records also. So we know that there's an address, and here the address is at the granularity of just a city. So we have city, state, and country. And then also for that, we create a location, which is a geospatial location. So there's a point data type. You can pull out the address from both of these data types and say that, okay, a manager is located at some address and the company is located at some address. Yet another opportunity, if you're building an agentic workflow, this is yet another opportunity for having a different strategy for how you can find information. So if you want to ask questions about companies that have been invested in by investment firms that are nearby or in the same city, that's a very simple pattern match. It is simple to express and also very efficient to run, which is the reason that you do it. Sometimes pattern matching is more efficient and also more understandable and more accurate. Sometimes it's nice to be able to do some sort of a geospatial index or sometimes a vector search. The geospatial index ends up being useful if you want to ask questions like, given a company, who's within an hour drive, what investment companies are within an hour drive. So they're not in the same city. You don't want to go looking through some kind of geospatial, routing, maybe across some highways or anything like that. You just want to find, as the bird flies, who's nearby within an hour. You run that as a geospatial nearness query. So you do kind of a point radius query, and you can find that as well. So you've got a couple different options here, either pattern matching, geospatial lookup, or again, because we put full text there, full text is there as well. And of course, vector search for all the text. So what is that? 5 or so different strategies for how you can already, query this particular database. To connect that pure data, the managers and the companies, to the unstructured data that we had, there's just one more relationship that you add. We know that each of these companies filed those forms. And so go ahead and create those relationships. You go through all the companies. We know that they filed some form, connect them. And now you can combine all the different techniques. So whatever technique you started with, you can expand context into the other parts of the graph, or you can use the graph to actually do a query and then find text that might be relevant. So you got to either start with some pattern matching, then find some text, or find some text and expand the context. In either case, you then also get an opportunity to do some ranking, where ranking ends up being a function of, so initially, let's think about like vector search. The typical thing with vector search is that you end up with things that are most similar. So like the similarity score is very nearby, right? So that this particular question that somebody asked has a very high similarity score with the chunk that maybe you found. that might be true, but that chunk may not be the most relevant or the most useful for the particular question that was asked. You want to have some other ways of actually deciding what is the best chunk. In graph theory, the most popular way to think about like how you rank lots of different text, which we all know from Google, of course, is by running PageRank. You could run PageRank on all those chunks, and if we know that some of those companies actually refer to each other in their filings, you could find out actually what is the most relevant text. Or you could find out, if you don't care about something like PageRank, you could also say that you might end up with a section of text that is the most relevant, but is not from the company that you asked about. So you might ask about, let's say, Apple again. It might be some other company actually discusses Apple in their filing and has a higher similarity score when you do the vector search. But you don't want some other company's opinion about what Apple's business is or what the risk to the business is. You want to actually backtrack all the way to make sure that the chunk you found is filed by that company itself. So you actually want to go all the way back to Apple and use that for helping to rank the results you get back. So that again, when you pass it back to the LLM, you feel the most confident that the answer or the context you're providing to the LLM is correct and factually true. And then the LLM can do with that, what it will. Okay, so this is the process that I went through. This is the kind of the summary slide. If you're going to take a screenshot of only one slide, there's maybe two that are worth screenshotting. It's the data model itself of what the graph ends up looking like. And this is the process that I ended up going through. If you look through the notebooks, you'll see this kind of in detail. There's a few different versions in the notebook that we'll take a look at. But it starts with creating the chunks and creating vector embeddings for those chunks, turning those into a linked list, and then adding a form node for each of those chunks so that we have the form itself, creating a summary on that form, another vector embedding occurs there. And then we add the structured data, both in the public companies and in the investment firms. For those, we get the full text indexes. And then finally, we pulled out the addresses and added a geospatial index. So that's at least 5 different strategies available for different kinds of questions that you can ask of this particular knowledge graph. And again, you should let the questions that people are actually asking drive what you do, but there's even more opportunities for how you can continue to elaborate on this. We haven't even delved into the text itself too much to actually pull out information. So there's this idea called named entity recognition. You'll hear the term NER sometimes mentioned, or named entity recognition. That is going through some text and asking the LLM, hey, given this text, what are the people, places, and things or topics that are interesting here? Can you please tell me about them? So you can actually pull out information there. And then for those things that you pull out, you can also then try to reconcile whether, let's say, ABK is mentioned in some of these filings. I don't think I am, but let's say that I am. Maybe ABK appears somewhere. Is the ABK that appeared in a filing over here the same as the ABK that appeared in some other filing? Well, might be or might not be. It depends on the overall context. And so there's some bit of a technique around also trying to reconcile whether the entities that you've pulled out are the same entity, and actually, bringing those back together so that they're not separate. If they are the same one, you actually want to have them linked. So there's a whole, avenue of possibilities there. We're not going to get into the details today, but that's an interesting topic itself. Then, of course, you can add more form data, other forms that are relevant that you might want to ask questions about. You can add any of those kinds of things. And all the way back at the beginning of this, I mentioned keeping in mind that somewhere there's a user at a keyboard who's entering things in. Keep track of what users are actually asking and give them the opportunity to thumbs up or thumbs down the replies that they're getting. Record all of that, factor that into when you're doing strategies, for how you answer questions, whether the particular strategy worked or not, and whether the particular answer was good or not. Allow there to be a feedback loop and capture that inside of the knowledge graph itself, that over time, the knowledge graph becomes better at answering questions because people have basically been curating both the strategies and also the overall, the quality of what you've got inside of the data. So keep all that, keep the feedback, keep the users' chat history, all those things are fantastic. And this ends up being a really great, powerful way to actually do any kind of domain. All these techniques, even though we're dealing with the SEC data here, this is pretty common across all things that we've seen at Neo4j when people are doing this in practice. You have some unstructured data, some structured data, find ways to connect that up together. Then also you expand from the unstructured data into the structured data. So you have a combination of both sort of identity links between things, but then also some things that you're pulling out that I was describing with the named entity recognition. Okay, that has gotten us all the way around. Oh, good. This is perfect. In just under an hour. to the final slide here. I'm going to pause here before I get into the notebooks and before I try to have some technical difficulties with switching over. Are there any questions that I should try to answer that have come up? Look through the comments. Okay, I think we're good. Cool. So then what I'm going to do next, actually, I won't go to the thank you. I'll leave it here while I try to figure out how to switch my presenting over to my screen. And I've got a VS Code open. Okay. If you've been able to, oh, right. Let me do two things. So if you've been able to go get this GitHub repository, you should see basically what I'm seeing here. And as I'm looking at the syntax highlighting in the file list here, I realize that I have not committed my changes and pushed them out. So let me go do that first. Oh yeah, okay. So let me make sure that's true. What have I been doing today? Oh, right. I can't quite see this. Let's see, I revised the driver interface and simplified the model fields. I think that's mostly what I was doing in the last couple of days. Probably not the best git commit message, but that's enough. And so I just pushed that out. So you'll have now available exactly what I've got. So if you've already cloned the repository, please go ahead and do a git pull and get the latest stuff. Okay, let me close this because that's going to take up too much screen real estate. And I'm going to go all the way up to just this MVG, the minimum viable graph part of this. And way up here at the top. Okay. When you look through this notebook, it has reasonable descriptions along the way for describing what each step is and what's happening. I guess one thing that I'd done just a little while ago that I hadn't commented too well is I've realized each of these notebooks have a lot of replicated cells at the top. I ended up creating a shared notebook here that basically imports from the environment what I need for actually connecting to a Neo4j database. It also has, let me take a look. Do I have the example here? Yeah. So these are the basic environment variables that are necessary. The connection to Neo4j. So if you have Neo4j installed locally, I'm running something called Neo4j Desktop, which lets you run and manage Neo4j databases on your local machine. Because I travel a lot, I like to have that portability. If you prefer to work in the cloud, you can get a free instance of Neo4j off at a thing called Neo4j Aura. There's a free level that you can get just by kind of signing up. You'd end up adding your connection string here, what the username is, the password, saving all those things. The database is the default database Neo4j, so you don't have to worry about that. You do also need an OpenAI API key. I'm not revealing mine in this video today, but this is where you would paste that in, and that would get loaded. And there's a data directory as well, and I guess in the template it defaults to being single. In the data directory, there's a couple different basically sizes of databases that are available, depending on I guess your appetite for spending money with OpenAI. If you just want to experiment with things, the smaller sizes are nice because you can get an idea of what's going on and how to do work without spending a lot of money making API calls to OpenAI. The sample size is my favorite one to work with. The sample size has 10 publicly traded companies, and then I think a few hundred management firms that have invested in them, and then kind of all the rest of the stuff. So I usually end up changing that. Okay, the shared notebook loads that environment, imports a bunch of things. These notebooks all use LangChain, which is probably the most popular, what's called orchestration framework for doing Gen AI applications or RAG applications. If you haven't gotten in any of this work before, if you haven't done anything, most of the work that happens is in Python. So if you're new to Python, welcome. And if you're doing work for the first time with this is very similar to just using any kind of it's at the same level, I guess I would say, is using like an object to database mapping layer. And there's lots of different variations on that. It kind of sits at the same part of your application, where this is the interface between your application and the services that you're using, both the database and in here also the LLM. These notebooks are set up so that if you want to host a local LLM, you can do that. So I use Ollama for that. Ollama installs on most different platforms pretty easily. Again, I think in your environment variables, you'd have to set that up. But then this ends up selecting which environment to use and which LLM as well. Right. And for some of the other stuff, so this is one extra key. If you want to get it, you can get a Google Maps API key. I end up calling out to Google Maps for doing the geocoding. So if we're given an address, when I'm creating those address nodes, I call out to Google Maps to actually get the geocoding for what the lat long is, and also breaking down an address into kind of like its city, state, and things like that. Okay, so the shared notebook basically sets things up. It figures out what the embeddings API is going to be, whether you're using Ollama or OpenAI calls, all that kind of stuff. And then it has some utility functions as well. You can look through that. The main point here is that this is common across all notebooks. To start off creating the minimum viable graph, I go ahead and load that shared notebook. And the first thing I do is actually, let's go ahead and give this a run, make sure that this is working. So the shared notebook is very, very slow to run. I guess the streaming takes a little bit of a toll here. Great. You can see the text model that I'm using OpenAI with text embedding Ada. It's kind of the default one for doing text embeddings. And for doing the chatting itself, I'm using GPT 3.5 Turbo. It turns out 3.5 Turbo for many things is pretty good. You don't need to use the latest, greatest models, unless you'd like to. They end up being a little bit more expensive, of course. So I, for most of my work, stay with 3.5 Turbo unless I have a need to go past it. Then the first thing I do here is actually just do a little bit of a sanity check. This, in the shared notebook, this GDB ends up being a driver that talks to the Neo4j database. And I'm just asking it to execute a query. Here, the query is the simplest thing that always is going to work is if the database is there and we have a good connection to it, just return hello world as a message. And, that's what we get back. So that's pretty simple. I'm not going to go through all the detail here. Like a bunch of these cells kind of take the time to go through step by step, looking what the data files are and doing some processing on them. The first bit that ends up being useful is doing the text splitting. So here I'm just using from LangChain their recursive character text splitter. So this basically has a strategy for how to chunk up text by, you give it an ideal chunk size, and then it tries to find more or less paragraphs or reasonable kind of text units that fit within that chunk size. So it tries to maximize the size, but honoring things like sentence breaks and paragraph breaks as well. And I'm not going to go through that demo either. There is then, and actually, I'm sorry, I'm going to back up for 1 second. The notebooks that are here, in this KG construction environment, so the 1 to 5, go very, very particularly slowly through the entire process of creating the graph. So what I talked through in the slides, this goes one step at a time. Let's create just this one thing and then add some things to it. So it's the create, enhance, and connect. Each of these notebooks does exactly that. One consequence of that is that there's a lot of extra boilerplate code to be very slow in particular. I'll take one quick aside here to note that there's where is it here? There's also a single Cypher file. So this kgconstruction.cypher, this is all just Neo4j Cypher queries with some comments as well that does the same thing, but it does it just on the database side. So you can just take this query, put that into Neo4j. It's a multi-line query. Each of these lines run, and it creates all the indexes you need. It does all the lookups for creating the vector embeddings. It actually does the text splitting all perfectly in Cypher as well. It's not the easiest thing to read if you're not familiar with Cypher. So I don't recommend this if you want to try to learn Cypher, but as a reference point for how to optimize, for how to do things very quickly, this is very performant. If you just run this Cypher, the entire graph gets constructed, within just a couple seconds, really bounded by the API calls out to OpenAI. If you're going to go through the notebooks, it takes quite a bit more time because you're doing a lot more work on the client side. It's much, much slower because you're doing one thing at a time, and it's all transactional. So it's create this transaction, and if you're doing 1,000 individual transactions, that's super slow rather than doing them all in one kind of bulk operation with one query. So that's one thing, just take note as you look at this by yourselves. Okay, back to the original part of this. There's some Python code basically for kind of processing through all the Form 10K data that we have, creating records out of those things, and preparing those for actually creating the chunks. In creating the chunks, and this I will spend a little bit of time on just for calling it out. In the slides, I mentioned how for Cypher queries, it's all pattern based. That's true both for reading and also for writing. So here I'm creating a Cypher query that instead of matching, I'm using a merge clause. So a merge is like an upsert, if you've heard that term before, where it'll do one of two things. You still give it a pattern. Here the pattern is, I'm going to call it things that are merged chunks. They have a label called chunk, and they have to satisfy these properties. The chunk ID has to be this chunk param chunk ID, which ends up being a query parameter that is passed in. This single pattern here that I'm highlighting will match any chunks that exist based on the chunk ID. So if you pass in a particular chunk ID, the merge will first try to find that chunk if it exists. And if so, you're all done, you found the chunk. If it doesn't exist, then it will create it. So that's the kind of upsert behavior that, if you're familiar with that, that's what a merge ends up doing. The merge has a subclause that you can do things based on whether or not you found something or you're creating it for the first time. So here I'm taking advantage of the subclause, saying, okay, if we've never created this chunk before, at the time of creation on create set, and then here's all the values I want to set. Again, this $ notation is what a query parameter is. So when you run the query from the client side, you're passing in a data record each time. And so I'm pulling from that data record, find the names, get the form ID, and set values on each of the chunks that you're creating. I create some uniqueness constraints. And actually, I'm going to skip over the kind of indexing part of it. There's, I think, enough text in the document to describe what that is. What ends up happening, let's see, let me make sure I think I need to get these helper functions actually. I probably want that one defined in this one. Okay, let me see if I can actually do this form import. I have not run one of these cells. Split form 10K data from file. Let's find that. Oh yeah, this big one up here. So these basically end up being a bunch of helper functions that end up calling down here. I iterate through all the files. They're just JSON files in a directory. From all those files, split the text, then create nodes for those texts, including doing the, actually, no, I don't do the vector embeddings quite yet. So here we're just creating the text itself, the chunks. Okay, so if I run all that and we're processing just 10 files, so you can see 1 of 10 all the way through to the bottom here. This is the last one that was created. 544 nodes were created because at the end of doing the import, I again do a pattern match just for chunks and then return a count of those chunks. This is a chunk count and basically print out the screen. So you see that it's printing out 544. Okay. So then there's some more sanity checking that you can go through here. You can run these queries if you want to see what this is doing. I'm going to get into the details. Here is where we get into the vector embedding part of it. That for doing the vector embedding, you can do that in one of two ways. You can either do that on the client side, directly calling out to your embedding API, whether that's, again, OpenAI or Llama or something else you might be using. Or you can do that within Cypher. As I showed earlier, there's a Cypher script here that makes those calls directly. If you're doing it on the client side, it looks like this. This embeddings API was created in the shared notebook. This is just part of LangChain. And I'm calling this embed query function. You pass it some text, and then you can see what the text embedding looks like. So if we actually just run this part here, there's two reasons to run this. One is just to demonstrate a little sanity checking that, okay, it's actually creating a vector. That's awesome. The other part that's useful is knowing that what is the length of the embeddings that are created. Depending on the embedding model that you have, the vector size is different. And so knowing what the dimensions are is really important. So here we print it to the screen, and we also save it to a variable that we're going to use in just the next step. And the next step here, I'm going to pass in that vector dimensions I'm going to create a vector index inside of Neo4j. Creating the vector index is what it allows us to do vector search. I want that vector index to match the same dimensions as the vector embeddings will be when we're calling out to the LLM. So this part is really important to make sure you've got that synchronized. Here, vector dimensions equals vector dimensions param in kind of what is that, title case? No, not title case. Anyway, in this case, matches the snake case of vector dimensions. This vector dimensions param ends up being available in this $ vector dimensions param, so that when this vector index is created, if it doesn't exist, 4 chunks on the text embedding of the chunk, have it be of these dimensions, and we're going to use cosine similarities, the function for doing a nearest query or similarity, right? So if I run that, the index gets created, it gets populated, and right, I've actually got, because I've run this before, sorry, right? So we've got 2 indexes here, the text embedding one that this one was creating, and also the summary embedding that I created just before starting this workshop. Actually, this index is already there as well, but you should see something like this when you're in this cell. With the vector embedding in place, we then go ahead and calculate text embeddings for each of the chunks and save those into each of the chunk nodes so that you then have the text plus the text embedding in the chunks. I'm not going to read through all the details here, although if you have any questions, please ask me. And actually, let me skip over for a second. And there's a question here from Diego. So I guess before we go on too quickly. Diego, you're gone. Okay, but you'll hear this on the recording. What would be your uptake on the usage of RDF knowledge graphs for RAG? It's a really good question. So part of the answer here is that the definition of knowledge graph varies wildly with the speaker. If you are used to thinking about RDF, if you've heard of RDF before, then those folks talk about knowledge graphs all the time. Particularly in the context of creating ontologies, like they think about it as being that is a representation of the world. It is an ontological view of the world, of course. So it's all about knowledge of the world. So there's a lot of knowledge graph terminology that's used inside of RDF. You'll see it as well, though, in like much simpler forms of graphs, that there are research papers that talk about creating knowledge graphs that are not creating RDF graphs, but they are simply creating graph structures that represent knowledge of different scopes, sometimes down to like word level, sometimes into sentence level, depending on the representation and what the researchers are trying to do. It ends up being different shapes of graph, whether they are very fine-grained or kind of coarse-grained. Different models have different ways of representing stuff. So the term means a lot of different things to different folks. The overall idea, though, is that you are using graph structures for representing information at whatever granularity makes the most sense for what you're trying to get done. And Varun, you've got another question here. I'll take the time to answer that now. What's the best way or the model you suggest to extracting entities and relationships from unstructured text? So there's a couple different approaches to this. And at the end of the day, actually, I recommend looking for a tool that does it and does it the way that you would like to. We ourselves, Neo4j, are working on a tool, a knowledge graph builder that you could take a look at. The basic technique ends up being that you take some text, you ask an LLM, hey, from this text, can you tell me what's interesting in this text? Can you tell me about the people, places, and things? There's a lot of very careful prompt engineering involved in doing that well. And what you're doing at this point is basically using the LLM as a really powerful NLP or natural language processing pipeline. NLP has been around for forever. But it turns out that LLMs are just better at NLP than most NLP tools. And so whatever pipelines might have existed previously are kind of being replaced by just asking an LLM to do that work. They're just really so good at language and language recognition and pattern recognition. So they end up being super at being able to find very unique things within the patterns, like names, and understanding that that's a name. Actually, later on, I'll show an example of like few-shot learning and where that shows up. Their ability to kind of recognize repeating patterns is so powerful. But so to answer your question, Varun, you can use a tool, I think, is the right way to do it. You can build it yourself with some good prompt engineering and having kind of a workflow of calling out to an LLM and taking the results you get back from that to create a new graph. but I would use a tool for that. And what I'll end up doing is pasting some links in the show notes, if there's an opportunity to do that, about some tools that are available. Cool. Thank you, Surya. Thank you for the kind comment. All right, I'll get back to the notebook and we'll get through some of this. Oh, wait, okay. Oh, okay. Since the questions are coming out, I'll pause on question answering for a little bit here. Like a good LLM, I will be prompted and respond. I might hallucinate. Who knows? What about connecting cross chunks between different forms? Is there a way different kinds of different kinds of relevancy between chunks other than predefined edges? Yeah, so the cross chunks I think are super, super helpful. The chunking that we have in the notebooks that are here, it recreates things into a linked list. You have the sequence of chunks. The previous and next chunk often are helpful for a complete context, but I do think that the cross chunk, the hidden relationships inside of the text itself, are really powerful to have, and they fall into two categories of things. It's the named entity recognition that we were just talking about, actually trying to find the people, places, and things through some natural language processing, basically pulling those out into separate nodes and then connecting those to the chunks, and then allowing the chunks to basically connect to each other by connecting to those concepts, people, places, and things to other chunks. That's super useful. And that's one category of things. The other category is you can do a little bit of NLP to do this, but is almost more successfully done with regular expressions, actually. Like there are very reliable identities often in many texts. URLs are a great example of that. But sometimes you might, find like forms have very particular IDs and ID structures. Depending on the documents you're starting with, they're often very useful specific exact identities in the text itself. That's probably better to be done with a regex than it is with an LLM or some kind of NLP pipeline. Go through, find those things, and whenever you find them, pull those out and actually use those as references for connecting chunks to each other or connecting documents to each other through those references. For some of our customers, I should say, that ends up being almost the primary thing that they do. When folks are dealing with, I guess, a common use case, and this is somewhat similar here, is that people have legislative documents that they want to keep track of, and that they want to correlate this kind of unstructured text in the legislative documents with internal policies, let's say, that they have. So the context here is usually one of compliance. Most industries have some level of compliance that they have to worry about and be aware of. Depending on the size and sophistication of the organization, they have very formal ways of actually making sure that they're compliant. And one of the things that they need to do is to keep track of legislation. And when legislation changes, they need to know what the impact of that change is. And that impact ends up being two things. It ends up being that legislation is often referred to in other parts of the legislation. So you want to be able to trace out to find out, okay, what are the other parts of legislation that are affected? And then once you've kind of found the areas of the legislation that have been affected, you actually then go from there into your internal policies, if you're the sort of company that has a compliance officer. And you find, okay, here's our internal policies that correlate with those legislation changes. We know now that we have to go evaluate our internal policies and see what adjustments we need to make to reflect those new changing legislations. So that ends up being very common. And you end up needing really a highly structured, very specific references between the legislation itself, like within it and across to other legislation. I hope that helps, Mustafa. Let me know if you'd like some more details about that. Okay, I'll switch back over to the notebooks in the meantime. And we've gotten as far as just creating the chunks and now creating the text embeddings for each of the chunks. Did I run this? I guess I did not. Let's run this down and see what happens. Oh, okay, great. Was I smart here? Oh, I was. Okay. So I took one extra step here to make sure that I could run this repeatedly without incurring basically a higher OpenAI bill. You'll see that in this cipher that I write here, when I do the pattern match to look for the chunks that I want to do text embeddings for, I just find all the chunks where the text embedding is null, which means there is not yet a text embedding on that chunk. So I only look for those chunks and return the text and the chunk ID into what here ends up being kind of a list of all those things, right? And then I use that list, which ends up being only the ones that don't have text embeddings. I then iterate through that list in the second half of the cell, iterate through the list and create the text embeddings and then save it. So if I run the cell over and over again, it's only going to do the things once. This part here is maybe not for the faint-hearted. Certainly if you're new to Neo4j and haven't done any of this kind of querying before, this looks pretty intimidating. But let me walk through this a little bit line by line. What's nice about the outcome of this Cypher query here in the middle, that this is the part where I actually go through, find all the chunks that I've got, and put them into order based on their sequence ID. So as I was creating the chunks earlier, I was preserving the sequence ID in each of the chunks so that I could separately later on in this cell here, go through those chunks, find them again, put them in order based on their sequence, and then create the linked list. So the couple of steps that are going on here are find all the chunks for a particular form. So it's find these chunks where the chunks form ID is the same. So I know that they all came from the same chunk and from the same form. And also that those chunks came from the same item within that form, because we've got multiple parts of the forms that we've pulled in. So for each of those, there's a separate sequence. So chunks that are in the same part of the form from the same form, bring those all together, basically order those based on their sequence ascending. And now that I've got those, this next couple lines here, I collect them all up into an array and then say, okay, in that array, just create a linked list by making this call to apoc nodes.link. This call here creates a linked list out of the array that I've given it up here, what ends up being the section chunk list. There's documentation on this online. This is not something you do very often. And here it's a bit more confusing because it's relying on having done previous steps separately. Again, if you look at the full Cypher KG construction here, that all happens on the fly as I'm creating things. I don't need to go back later and collect things up because I already have all the chunks that I need. So this is kind of like a post-process way of doing it. In the Python, what I end up doing is, I know that I've got these different item names. So I iterate through each of those item names, pass that in as a query parameter along with the form that I'm working on. So I go through all of the forms, and then for each of those forms, each of the different items, which are different sections of the form, and then execute this query to create these linked lists. Okay, I'm going to jump forward here. So there's some fun you can do if you go through this notebook. You end up creating that kind of initial linked list version of a knowledge graph. It is, again, the minimum viable graph. Each of these subsequent notebooks from that first one basically take the same path that I followed in the deck. So if you look back at that deck, I had that one slide that talked about each of the different steps. They more or less correlate with exactly one notebook, where you can go through the notebook to figure out step by step exactly how things are done. And again, I've broken things down so that as you look through this, it is do just one bit at a time. Like, for example, here, this is just text processing in Python. There's nothing clever happening in the knowledge graph at this point. There's a lot of helper functions that are here to kind of make things a little bit easier as you put things together. But then you'll see the queries, and this will give you some idea of like how the queries actually work. If we jump forward all the way to the kind of the end here, and this is the part where I'll be spinning the dice a little bit to see that the demo gods are being favorable. I should have a Python environment that is up to date. That seems good. Still connecting to the local database. Cool, same models and things. Okay. This final notebook here, this notebook number 5, chat with the KG, chat with the knowledge graph. This is where you get to start having some fun with actually doing queries. So you've created the knowledge graph through these first 4 notebooks. It's at notebook 5 here where you start to run some queries and see what the results end up looking like. In this first one here, I'm taking advantage of the full text index so I can do arbitrary lookup of companies by their name. So here I know that there's a full text index called full text manager names. I'm going to look for a manager name called Royal Bank and see what result I get. So I found the Royal Bank of Canada. Shout out to Canada. Be loud. You guys are from Canada, right? Just happen to find one of your banks here. That's cool. And you can change this to anything, right? So Royal Bank of Canada. Let's see, what are the managements? I know there's like, is it called BlackRock? Right. Okay. So you can basically add, this is full text search. So any kind of name here that might show up, you can just do a full text search. This is going to run the search and return any of these results, I guess I should actually say. Oh no, I'm sorry. I'm limiting it to just one. It'll return the top result that correlates with what you've done through the full text. So great. We can find arbitrarily named investment firms. If I want to continue with Royal Bank here and find the location of Royal Bank, and now Canadians, I would love to get some verification of this. Is this actually true? This is running the same full text search here at the beginning. I'm going to do a full text query on the full text manager names for Royal Bank. And then once I've found that, I'm going to use that as a manager, do a pattern match, and look from that manager that it's located at some address, then return the manager's name and the address. So the manager name is Royal Bank of Canada, and the address is in the country of Canada. So far, so good. It's in Toronto. Is that true? I hope that that's true. Is Ontario the state of Toronto? Canadians, I'm going to rely on you there. And I don't know who can verify this, but the lat long should be -7943. So we've gotten from the full text search, we've reached back through pattern match all the way to the address and then returned all those values here. You can then start to ask fun kind of analytical questions. And again, this is so far, we're not doing natural language anything quite yet. This is just querying the knowledge graph directly. And later on in this notebook, you'll see how to take these patterns and actually map them to natural language. So let's just go through just a couple more here first. So if we want to say, which state has the most investment firms, that's a pattern match first. We're looking for managers that are located at some address. And then we're going to return things in a particular way to kind of get some notion of like what the most means. So we return address to state as the state. We've asked for which state. It's okay. We want to return that. And then we're going to count each of those states. So it's the occurrences of that state, basically. We're going to do kind of a grouping by state. So counting address.state as the number of managers, and then order by the number of managers descending, limiting it to 10. And KG is not defined, because I did not update this part of the query. So let me fix that. And Copilot, I don't really want your help right now. So this is done wrong. That should look like that. Oh, and actually, let me this is what I get for updating things on the fly. Okay, cool. So I've switched my interface from what was called the knowledge graph interface to the raw kind of graph database interface in these cells. So just running this query directly, here's what the results end up looking like. In this sample data set, at least, there's 304 managers in New York. You can see the rest of the list all the way down to some investments management firms in New Jersey. And I see I've made this mistake a couple of times here. I haven't updated any of these things. So if you're following along and your queries are not working, you can fix exactly the same thing that I'm fixing here. Change that and get just the records. And so this was instead, so the previous one was looking for in the investment firms. This is looking for the publicly traded companies. Same kind of a pattern match, but starting with companies, and the same idea for the return, accumulating them based on the state, and then showing what the results are there. You can go through each of these different queries, updating this part in the beginning to be the right interface until I make the push out to GitHub, and see the different kinds of results you get. Looking back, if you have a kind of a screen grab of what the graph looked like, you'll remember that each of these things, so manager located at address, this is just a pattern match looking through that overall kind of graph that the graph schema that we had in one of those slides. So you can, look at what the possibilities are in those slides and actually just change this pattern to whatever you'd like to, add a where clause for things you want to actually qualify. So here I'm doing a where clause on the address. So the address is being saved in this address variable, let's call it. I'm saying where the address.state is California, return some things about it. This is enough to know, I think, to kind of just start experimenting with like what kinds of queries you might be able to do through some pattern matching. I'm not going to go through all of these, but they're all, prefaced by like kind of a hash comment about like, what is the question that's being asked, and then how do you actually execute that question. That becomes useful later on. A variation on that, because we add geospatial indexing, at least to this data set, is doing point distance, so radius distance from a point. Very similar idea here. You could look for a particular address that's, here at the city of Santa Clara, find that address, then do another pattern match where some companies that are located at a company address that, right now is unqualified, except that we want the predicate of this point distance calculation to be based on this address location, which is the original. Here it'll be Santa Clara, whatever Santa Clara's address is. And through this pattern match, we'll get a company address location as well. The point distance will do a Cartesian product, or not Cartesian product, I'm sorry, Cartesian coordinates calculation here, a distance calculation. And then see that is less than 10,000. This is based in meters. So whatever meters you want to calculate here for the distance, run that as a query and find things that are based on nearest in terms of geospatial location. And again, you can kind of combine this through all the different patterns that are possible. Take advantage of full text, plus doing some pattern matching, plus some geolocation, combine it in any kind of ways that are reasonable. And again, what's really interesting here is that these different kinds of questions that people ask, or that are askable, I suppose, this hopefully be driven by either your curiosity or your anticipation, or by your actual feedback that you've recorded about people trying to ask questions that aren't answerable, that where the LLM either comes up with something that's wrong or actually is honest about it and says, I don't know. And then you can actually look at different strategies for how this might be answerable. Here, I'm kind of taking the manual approach of saying, okay, let me go through a bunch of different examples. And then later on, actually in this next section here, this is where things get kind of fun. It turns out that GPT 3.5 and definitely 4 and a lot of the code-oriented models are pretty good at generating Cypher, because Cypher is a pattern-based query language. So if you provide it with enough kind of expectations, and here this is a prompt template. Here's a prompt template that says, hey, LLM, you're really good at generating Cypher. I'm going to tell you about a particular graph that I know about here. The schema of the graph is going to be passed in. Please generate some Cypher queries based on a user question that's going to show up. But before you do that, I'm going to give you some examples of Cypher queries that you might be able to write. And this is what's called few-shot learning. And this, if you look at this part here, this mirrors exactly what I was doing in each of the cells. Hashtag some natural language question, and then here's the Cypher to run that question. Earlier, I'd mentioned that the pattern matching is really powerful with LLMs. They're pretty smart about realizing in this example, this is, as we said, here's some examples, right? So it knows that this is an example. And it is also able to pick up that, hey, San Francisco here probably is the same as San Francisco here. So that if you ask this kind of question, but put something else in place of San Francisco, usually it's pretty good at actually replacing whatever literal string is here with the literal string that was passed in by the user when it's generating a query. You can look through each of these examples. Most of these correlate with some of the previous cells that we went through. If you come up with some new, I recommend kind of experimenting with this a little bit. So start with writing your own Cypher queries for answering different questions, and then add them to the few-shot learning here. So as you come up with interesting questions that don't come up with good answers, add them to the few-shot learning and see what you get. The last part of the few-shot learning is you give kind of the prompt part of it here, like here's your instructions, here's some examples, and the very last part is, and okay, here's the user question itself. Given this user question, go ahead and generate some Cypher. I use LangChain for this, but I have not imported all the files I need. So what have I skipped over? Sorry for scrolling quickly. Where did I import the LangChain parts? Oh, where did I not add that? Oh, and I'm going to have to go figure out where I get what the import is for prompt template. Okay, so I'm going to go switch over to the comment section first and see if there's any questions. And if there aren't, then we'll debug this together. Okay, so no questions yet. I'll give you guys a minute to ask me some questions before we do live debugging. Okay, I will switch back and forth a couple times. So prompt template, where should I be importing that from? Oh, I do have it here somewhere. Oh no, that's just the error. Here's an example of importing it. I probably want each of those things. And is it in the shared? Let me add it to the shared. Let me try to fix this up. So in case you guys actually try this out. Yeah, let me add it here. So import all the things. I'm going to save that and then reload it here at the top. That should get me all the imports I need. And where was the, down here somewhere. Okay, let's save the template again. And let's see if this works. What did I do? Oh, there's, okay, so it's not just that I imported those things, it's that kg is not defined. Why is it? Oh, because I stopped using kg. Right. Okay, I should not have been changing this an hour before starting the workshop. That seems like bad practice. Let's see, what's an example of me creating the knowledge graph? What does that interface look like? kg equals. There's an example of me creating it. Let me just steal that. Always easier to copy and paste. This is the hard reality of our lives in doing software, right? There's an awful lot of copy paste because it's just easier. Okay, so down here, I'm just going to do it in line here. Okay, that seems good. So let me see if this actually runs now. So if I run this chain, if I ask this question, which investment firms are in San Francisco? The way I've set this up, I've set it up to verbose is true, this graph cipher question answering chain. Again, this is a LangChain implementation that's available to you if you want to use that. If you set this verbose to true, you get some really nice debugging as it's going through its process. So I asked what investment firms are in San Francisco. Here's the cipher that was generated. It's doing a pattern match that for the manager who's located at an address where the manager address.city is San Francisco. Fantastic. You can see that the LLM has taken advantage of, the pattern that we've described to it, but it's taken some liberties here, like manager address. I don't think is the variable that I used before, but that works just fine. Just to kind of sanity check here, let's say Santa Clara and run that. Oh, nice. Okay, it tried something different here. Why did that fail? So it tried a different query. So a manager who's located at an address where the city is Santa Clara. So that looks correct to me. That should be true. But maybe there's no management companies in Santa Clara. And what if we say something like, and this is where the experimentation gets fun, right? Okay, so there are definitely ones in New York, and it's gone back to writing this in a different way. Why it chooses the two different styles, I don't know. It's ignoring my examples. Oh, but it is also returning manager.manager name, which is not actually a field that's available. This should just be manager.name. So it's gotten that part of the schema wrong. In production, and this notebook doesn't have these extra steps, if you're taking like an agentic kind of approach to this stuff, you'll end up with a workflow. An important part of whenever you're using any kind of natural language to query generation, you give the LLM lots of context, you give it some few shot examples, you try to give it actually maybe not even the full schema, maybe you give it kind of a very precise schema that is only relevant for the question that's being asked. There's a lot of strategies involved even at that point. But then you let it generate a query, and you shouldn't just run the query straight away. Here we do just generate the query and then run it. You should probably take the result of that LLMs generating the query and make sure that it's syntactically correct, so that it's at least not wrong. You should probably also put in some rules about making sure that it's not, trying to destroy all the data. If it happens to have permissions, that would be bad. You can, of course, put permissions into the database and make sure that when you're integrating with the database, that the LLM is limited to just read-only access. For example, that would be a smart thing to do. You can put any kind of security rules you want to. Neo4j has full, role-based access controls, so that you can even have access that is based on the user who's asking the questions. So it's possible that if you would like to, for your context, you could actually let a user create data through natural language interface. For sure, I would have lots of guardrails in place if you were doing that, but take advantage of that or avoid it as is appropriate for your context. Here again, like what I also recommend is check that it is syntactically correct, that it matches the permissions that you expect, that's not doing anything dangerous, then run the query. When you get the results back, it's worth doing another round trip with the LLM saying, hey, given this user question, and you ignore all the other stuff, just like given this user input, is this a reasonable answer? And do another check, basically they're kind of a final sanity check. And then say if that is true, then pass it back all the way to the user and say, okay, great, we've got a final answer for you. Okay, and this is an example of something that ended up failing. Let's try this one more time. Let's go back to what's another city that's here? Oh, it wasn't Toronto. Few things in Toronto. Nova Scotia, Toronto Dominion Bank. Awesome. Their addresses, things like that. Cool. So you can do some querying. And again, it's because you've got the LLM, there's a bit of chance involved to put in the guardrails. This notebook isn't being very safe right now. You can explore any of these things. You can ask any of these kinds of questions. And then based on modifying this few shot learning bit here, change the kinds of questions, maybe add some more examples of how to answer those questions. If you're playing around with the cipher as well, it's worth spending a lot of time to kind of really explore the variation of questions you might want to ask or allow people to ask, and like what it is that you can actually have for a strategy for answering those things. Okay, I'm going to switch over to one last notebook, which is, where did I actually put it? Oh no, there should have been, okay, yeah, finally, I moved out over to here. Okay, there's an entirely separate notebook. So this is all just in the KG construction directory. There's another notebook called, in the RAG example, is just one example there called compare QA chains. For kind of side-by-side comparison, I think this is really pretty helpful to do as you're developing stuff. If you have any kind of an agentic kind of workload that you have in mind, you're going to spend a lot of time in kind of debugging and trying out what the different strategies are, how to pick different strategies, how to move through a different workflow, whether you're creating tools or letting the LLM choose the tools, if you have rule-based ways of deciding what tools are running. At some point, it's worth having things run in parallel. That's what this notebook does, is it goes through all the things that the previous notebooks did and what's possible for different ways you can query the database, and combines them all into like one query example. So if we go down here to the bottom, it does this in a couple of different ways, again with a few shot learning here, and then it basically builds this function at the end. This function, compare all question answering, follows a couple different approaches, doing pure vector search, a vector search with the context window, that's the kind of linked list approach, then a vector search with the graph pattern match, that's from the chunk that you have, find some structured data that you think might be relevant, pass all that back in to the context, and then finally using the text to cipher approach. With this in place, you can then run this function, compare all QA, and ask all these different kinds of questions, and kind of look yourself, kind of eyeball, like this is the human in the loop part of it. Evaluate yourself which questions look the most appropriate and most useful, and also sometimes which are the most correct. If you have a kind of any kind of a eval framework that you're using, this is what you want to end up, qualifying, like the questions you encounter here. Add that to your evals you have. Here's the questions I'm asking. Here's the expected answer, and make sure that that kind of stays in place as you're evolving your overall strategies. You can see I've got a whole bunch of different kinds of questions that are here. I'm not going to go through them right now, but I encourage you to try this out and see what you get. Okay. Back over to the comments here, and I'm going to open up for questions a little bit. Varun, hello. What if the relationships in the Cypher query that LLM has produced is not exactly the same that is created in GraphDB? This is not going to fetch any results, right? That is correct. Yeah. So when you're doing this syntactic check, there's actually two things you're able to check just kind of on a rule-based fashion. You can check that it is correctly formed Cypher, but also that the labels and the field names, the sort of the property keys and the relationship types, you can check that those are all true and correct as well before you try to run things. You can see that it is well-formed Cypher, but also that it is making the right references to like what is possible within the shape of the graph. So you can basically match it against your schema, validate that it is a reasonable query to run, and then run that query. Because you're right, if that doesn't match, then you're not going to get any kind of results at all. In Cypher, and the LLMs, when provided a schema, rarely do this. But if, for example, let me go away. Oh, I don't have any examples here. Let me switch back over to this one. If we're doing some of these simple pattern matches, like if you said, located at a, this is valid Cypher. This pattern is still totally valid, but because this relationship type here, located at a, doesn't exist, this pattern will never find anything, and the results will be null. You'll have no results, right? You'll have 0 records returned. So this has to be correct. It's possible, though, that instead of actually having anything there, like that actually will work. If you specify nothing here other than that there is a relationship from a company to an address, this is always going to work. So sometimes this is part of what I meant about the adding just enough schema. Sometimes it's helpful to provide just a fine amount of the schema. It's kind of a slice of the schema that matches exactly what the user is asking about. If it's not relevant for the question, then just company to address might be enough. And this pattern is more likely to be correctly generated than if you had extra detail here, the located in. If I can possibly even type it. This, again, depends entirely on the LLM that you're using, what kind of prompt engineering you've done, again, how much schema you've provided, those kinds of things, and also the examples that you've provided. So if your examples include this, then you're going to, I'm sorry, right, obviously this is in the part where you're including examples. If you include examples like this, it is more likely that the LLM is going to provide generate queries that match that as well and ignore that. And so if you underspecify here, knowing that it is correct, it is more likely to be generated properly as well. Let's see if there's any other questions. Cool. Okay. That's all I want to go through today. I'm going to stay on for a few more minutes and see if there's anything else that comes across in the comments. To my hosts, is there anything else you guys might want to learn about or anything that was piqued your interest?
From us, thank you so much. I'm someone who's not too technical, but I learned a lot. It was so useful. I'm someone who is not too technical, but tried to create chatbots and LLMs and try to use RAGs. So even for me, it was so understandable and easy to understand. Thank you so much for it. I wrote down some notes and I want to go through it again. I don't have any questions. If people who are watching have any questions, please comment down below. And once again, thank you, Andreas, for being here, for your time. This workshop is part of a hackathon that's going to happen May 10, 11, 12. It's 3 days of going from idea to MVP to having users for a product. The whole idea, we want to challenge you to build the billion-dollar startup in 3 days, if it's possible. We'll be having judges as investors at the end of the hackathon. So if they are interested in your projects, you will get investment from them on the spot. This will be a great opportunity to build something fast or learn about building something fast, experience it. I think we have a question. Could you please post a link for Neo4j tool for entity and relationship generator.
Yeah, so I will do that. And I have to ask, so I'm a little unfamiliar with the interface here. I'm not sure why it's not letting me comment. Somehow
I
because
think, yeah, if you can share it with us, just give me a second.
let's see.
Yeah, if you did want to share it on LinkedIn or here, or you can just post it and then we can copy paste it and send it to them.
Okay.
Yeah.
And this recording will be on, I guess, online as well. Like I can somehow just add comments to the recording, right?
Yeah. So
maybe that's what I'll do. Because
Perfect.
there's a bunch of things that I want to refer to. There's that graph builder tool. I'll post that. I'll also post a few different tools that are available for doing the named entity recognition, kind of that extraction process. There's a bunch of tools that are really useful that I'll put links to.
Perfect. Sounds good. Yeah, it's going to be on YouTube, LinkedIn, Twitter, and your LinkedIn, I believe. It's going to be like a post, so anyone can just like comment on and continue the discussion. I do encourage, well, not you, Andreas, because you created this, but anyone else watching this, any key takeaways you've had, your favorite parts of it. Something that stuck with me from the very beginning was that LLMs are like aliens. So people making them don't even know what's happening inside of it. It's like black box, and so far we're all safe and from it. But yeah, please share your thoughts and favorite quotes on it. And thank you so much again for coming in, Andreas. This was super valuable.
It's my pleasure. This was a lot of fun.
Yeah. Thank you. Well, you take care, and we're going to end the stream right now. Have a wonderful day. Take care.
Bye, everyone.
Bye. Thank you. Bye. Bye.